Hello everyone, let's solve some Leetcode today. So today we are going to solve Leetcode 269, that is Alien Dictionary. I'm using the problem statement from Leetcode's website because I don't have Leetcode Premium, so I cannot show you the description from the Leetcode, but this is actually the same problem on Leetcode's website. Basically in this problem we have a foreign language, or you can say alien language, which actually uses the same alphabets that we use, the A, B, C till Z, and they are pretty much the same. The only thing that is different is the ordering among those letters. For example, in our normal language, we have ordering like this. We have A, then we have B, then we have C, then so on till Z, right? This is the normal ordering that we have. We always say that A comes before B, B comes before C, C comes before D, and so on. But here in this language, the alien language or the foreign language, this does not have to be true. The ordering can change. They can have B, D, M, N, K till Z, right? They can have that kind of ordering, or they can have something like A, N, D, K, M, Z till the end of the 26 letters. So they can have any other ordering that they want. That is completely up to them. We have no control over it. Just like we decided that our ordering is going to be A, B, C, D, they decided that their ordering can be something else. Now we have a non-empty string of words from this dictionary, the alien or the foreign language dictionary. And in this dictionary, the words are sorted lexicographically based on the rules of the new language. Basically, based on the ordering of elements in the new language, we have a lexicographically sorted list of words. Okay. So first of all, what is lexicographically sorted? It simply means that we have words in a sorted array. That's all. Just like we can have a normal dictionary from Oxford that will have all the sorted words, in the same way, there is some dictionary in the alien world also that have all the sorted words. And we just took some words from that dictionary and placed them in the sorted order. Now, what is lexicographically sorted? Well, in the normal dictionary, the one that we humans use, we can have two words like ape, and we can have another word apple. Okay. Now I want to sort these words. How will I do this? Well, I will take the first character and compare it. They are same. Then I will take the another character and I will compare it. They are also the same, P and P. Then I will take the third character and compare them. Now as you can see that E is basically not same as P, right? And E comes before P in our ordering. This is the human ordering that we follow, right? So E will come after D, but it will come before P, right? So it means this word ape will be first in the ordering and then apple will come. Okay, this is going to be the order. First we will have ape, then we will have apple. Now understand that after this first change, okay, after this first different word or first different letter, these letters, they can be in any order in both of the words. The only thing that matters is the first character that is different. Based on the first different character, we will decide the order of these two words in a list. And this is how the humans do it. The same thing is applying for alien dictionary. They are also sorting their words based on this rule. It's just that their ordering is different, that's all. So if in their case, the P is actually before E, if that's what they decided that they want P before E, then in that case, we will have apple before ape in their dictionary. So this will be the ordering for them, probably. So that is what the lexicographically sorted means. It simply means that they have words in their dictionary and they have sorted those words based on their ordering, which is different from the human normal ordering, and those words are placed in the words array. Now we have to derive the order of letters in this new language or the alien language. If the order is invalid, return an empty string. If there are multiple valid orders, well, return any of them. So this is a good thing. If there are multiple valid orders, we can return any of them, right? But it also hints at the possibility that we can have an invalid case where we will need to return empty string. So what does it even mean for us to have an invalid case? We will have to look into it, right? So basically, we will have a lexicographically sorted list of words and we have to find out the ordering that aliens are using. Just like we have this ordering A, B, C, D, E, they can be using some other ordering, and that's what we need to find out. Okay. Now we do not need to find out all the characters of the 26 alphabets in their language. We just need to find the ordering of the letters that are present in this words array. So the words array will have multiple words and those words will be made up of letters. And whatever letters we found there, we need to consider only those letters to return the ordering. Now here we have a few rules. This rule is basically something that we have already discussed. This rule defines which word should come before the other word based on the first different character that we already saw here. This rule, the next one, is actually a little bit more important. So if the word A is the prefix of word B, A dot length should be less than B dot length. This rule is saying that if there are two words A and B, and A is actually a prefix of B, and A's length is less than the B's length, it means the word A should always appear before B in the given word list. For example, suppose in the normal language I have two words, app and I have apple. Okay, now here you can see that this word, A word, is actually a prefix. Okay, it is a prefix of this another word, which also means that the length of this word, that is 3, is going to be less than the length of this apple word, right? Because the length of apple word is 5 and the length of app word is 3. So if these two conditions are true, if a word is actually prefix of the another word and the length of this word is less than the length of the other word, this word with the less length should always and always appear before the word with the greater length in the lexicographically sorted list of words. So it means if inside of this words array we ever find something like apple and then we are finding app, this is an invalid order. Why? Because this is actually a prefix of this and length of this word is less than the length of this word, so it should be before this word. That is what this rule is talking about. And this is one of the cases where you will need to return an empty string, because this whole thing actually makes the word list invalid, so you can simply return an empty list. So how do we solve this question? Well, here we have an example. Okay, here we have a few letters like H, R, N, then we have F, then we have E, then we have just N and F again. So basically we have a few letters, that is H, R, N, then we have E, and we have F. So these are the 5 letters that we have based on the given list of the words. So we don't need to find out the ordering between all the 26 characters. We just need to find the ordering between these 5 characters. So try to think about it. How can we do this? What are the hints or what are the situations that the question is giving us? The question is saying that this list is going to be sorted, right? It means this is going to be before this somehow, right? And we know that it is also lexicographically sorted. So it means that these two words are actually sorted based on the first different letter. So what is the first different letter? Well, H and H same, right? R and R same. And F are not same. So these are the first different letters. What this means is that N is going to come before F. Okay, so you will have something like this. We have a pair N and F where we know that N is going to be before F, because in lexicographically sorted order, the word with the letter that comes first in the ordering is actually kept first and then we have the other word. Just like we discussed in the case of ape and apple. Since E comes before P in our normal human ordering, that's why we have ape first and then we write apple in the dictionaries. So we could at least find out this much. N always comes before F. So now let's look at the other two words. We have HRF and ER. What is the first different character? We have H here and E here. So we will take the H and E and we can deduce that H must come before E. In the same way, we can go to the next two words and we see that E is same, right? But R and N are different. So this implies that R must come before N. So R will be before N, right? Then we can go to these two words and we can try to figure out which one is different. So we have E here and we have R here. These are the first letters that are different. So we can also deduce that E must come before R. Now what do we do with these pairs? We have 4 pairs and we have a few letters. Well, we can try to connect them. So we know that N connects to F, right? H connects to E. R connects to N. And E also connects to R. Now I know that E connects to R, right? So E is here and E is also here. So instead of having this, I can simply say that E connects to R, right? And also we can see that we have a one N here and one N here. So it means that this particular N is basically the same. So if I try to make it better, it will look something like this. We have H here. I'm starting from here, okay? So we have H, then we have E, then we have R. Because we have E, then we have R, then we have N, so it will come to N. So we will have N here, and after N we have F. So I can just write it like this. We have F. So the relationship between characters actually looks like this. This is basically what we are able to connect. Now here you can see that we have something. It is basically a letter, but let's just call it something. It can be anything. A configuration, state, situation, place, right? So it is something. And then we have this rule. There is a rule that is allowing us to connect from H to E somehow. So what it means that we have something and we have a rule that is allowing us to go from one thing to the other thing, right? So I can simply call it a node, right? that something is nothing more than a node, and that rule is nothing more than an edge. So I can just convert this whole thing into a graph, right? Because that's the rule of graph. If you have something, and this thing can be anything, like a normal configuration, it can be state, place, position, whatever, it could be anything, and you have a rule that is allowing you to go from one thing to the other thing somehow, okay, then these two observations simply mean that you actually have a graph, and that is exactly what we have a graph here. Now this arrow actually represents the rule, that's why I'm just removing it, but we do have a graph like this that is starting from H and ending at F. It is a directed acyclic graph because we are allowed to go from H to E, but we are not allowed to go from E to H. Why? Because these edges are actually based on the rule of sorting, lexicographical sorting, the ordering between the letters, and that's why we don't have any edge from E to H again. So what this means is that all the letters that are present in the list are nothing more than nodes, and the property of sorting the letters actually helps us to go from one node to other node. And now a lot of you guys will be able to do this problem because it is a simple graph. That's all it is. Now you guys must be thinking one more thing, that hey Satyam, you are actually comparing this word to the next word. Why can't I compare HRN with this ER? And the answer is yes, you can. You can compare the first word with the third word and it will give you H to E. So there will be a relation from H to E also, right? And we already have this relationship right here. So let's take another example. We can have HRF and I can try to compare it with RFNN. So here I can see that H and R are different letters. So it means that there is an edge between H and R. So it should look like this, right? There is an edge from H to R. So you can do that. You can have an edge from H to R, but this new edge is actually not needed. Why? Because these edges are actually implicitly trying to tell you that hey, you can go from H to R. H will always come before R. That's what these edges are representing. And that is why we did not need to take an element and then compare it with all the other words in the list. We can take the two adjacent words and just compare them, because if you try to compare each word with each other word, you will have edges, like many edges, and most of them are simply redundant, like this one, right? We don't really need this edge because these two edges are implicitly conveying that we can go from H to R. So even if you have this other edge, it will not really change the answer anyways. Yes, it will make the calculation a little bit more messy, but it will not really change the answer. It will not have any effect in the logic. So this is the graph that you are able to create based on the given example, and this is a very simple graph, right? You can actually just look at this graph and you can figure out that okay, this is the ordering. Okay, so you have the H, E, R, and F. This is the ordering, or you can simply call it this is the answer. This is something that you can return and that will pass the test case. But let me tell you guys that not all of the graphs that you can generate are going to be this simple. You can have crazy graphs. Right now this is a simple linear graph, but you can always have graphs like H, E, then E will be connected to, like, just say F, right? Then H can be connected to here R. So this can also be a graph that you will find in the questions, and now it is not very clear which ordering you should take, right? Because you have two orderings. You can go from H to E, then you can go from E to F, and you also have this ordering that you can go from H to R. So you can write H, R, E, F, or you can write H, E, R, F. The only thing that matters is that H must come before E and H must come before R. Okay, so H is before E here and H is before E here. H is also before R here and H is also before R here. Now what is going to be the order between R and E? Well, that does not matter. Why? Because there is no edge between E and R. So we cannot say what is going to be the order between E and R. It can be anything. So both of these orders are actually valid. And the reason that we have F at the last is because we know that F must always come before E. And that is why if E is here, F needs to be here. Even if E is here, F will be here. Now here in this case, you can change the F. You can make it H, E, F, R. So this is also a valid ordering. Why? Because we have E after H. Okay, so E is after H. We have F after H. So F is also after H. And we have R after H here. So R is also after H. So that is why we have three ordering here. 1, 2, 3. So which one are you going to take? And yes, the question is saying that we can return any ordering, which is very good. But how can we even figure out these ordering? What is the way to figure out these kind of ordering? And so here is something that you should observe. So if you have two nodes, H and E, and there is an edge between H and E like this, that means H is going from H to E, then H should always appear before E in the given ordering. What kind of condition is this? This is a condition for topological sort. In topological sort only, if we have two nodes u and v and we have an edge from u to v, the u will always come before v in that ordering. So this whole alien dictionary question simply reduces down to topological sort of the graph. That's all you have to do. You will have a graph like this or like this one, and you just need to figure out the topological sort for that graph, and that will be your answer. Isn't that intuitive, guys? Now you can find the topological sort with the help of BFS, or you can find it with the help of DFS. Now DFS is definitely preferred way. Why? Because BFS is actually very cumbersome way. You need to keep track of multiple things. That's why usually people do not use BFS and they simply use DFS. Even though it is a recursive solution, it is a lot more simpler to implement, and that means you will have less errors when you are doing interviews. Now if you do not know what is topological sort or how to find topological sort with the help of BFS and DFS, I have already created a video completely explaining what topological sort is and how to use BFS and DFS to find the topological sort. So you can go ahead and watch those videos, but here I will simply give you a very quick short overview of it. So topological sort is nothing more than post order traversal. If you know what is a post order traversal of a graph, you know topological sort. So to find out topological sort with the help of DFS, you can simply do a post order traversal. You can start from the node and you will simply go to the depth of the nodes, and once you have reached a node that is a leaf node, you will simply take that leaf node and you will put it in a stack. Okay, so suppose that I have a stack here, I will put that node inside of the stack R, and then I will go back. Why? Because this is a leaf node, so I need to go back. I will come back here on the edge, and then I will go to the other branch. So I will go to the E, but I will not do anything right now. I will try to go to this left side, but it does not exist, so I cannot do anything, right? So I will simply come back easily and I will go to the right side. I will find a leaf node F, right? So now I cannot go here and I cannot go here because they don't exist. So I will take the node value, that is F, and I will place it in the stack. Okay. And then I will go back. I will go back to E, and I see that there are no more children or no more neighbors that I need to deal with for E. So it means the E is completely done. I will take the E, I will place it inside of this list, and then I can simply go back to H. Now H is also done. We have gone through the left neighbors and we have gone through the right neighbors. So H is done, and I will simply place it inside of this stack. And now we can simply keep on popping. We will have a string S and we can pop the element H, and then we will pop the element E, we will pop the element F, and then we will pop the element R, and this will be the string. This will be the answer that we can return. Simple as that, guys. All you need to do is get the post order traversal of your graph. That's all. That is literally all you need to do to find the topological sort for a given graph with the help of DFS. Now, yes, there are some edge cases like cycle detection. So suppose that we had a graph like this. We had only E and we had only R. Okay, so we only had two words in the given dictionary and we could only find two letters from those words. So we have E and R. So E will be placed before R in an ordering. But what if there was an edge from R to E? Okay, so we have a cycle here. We can go from E to R and R to E again, right? It's a cycle. Now this is an invalid case. Why? Because what does this even mean, right? If you say that we have E before R and then you are saying that we have R before E, so what does this thing mean, right? What does it mean? It does not mean anything, because in an alphabetical ordering, you cannot have the same alphabet come twice. So it means it is an invalid case. And if you ever see a cycle like this in the graph, you are supposed to return an empty string as answer. This is going to be the answer in this case. And so detection of the cycle in graph is very important, and you should go ahead and watch my video on topological sort to figure out how we actually decide whether there is a cycle in the graph or not. How do we detect the cycle in the graph with both DFS and BFS. So both of them have been explained. You will find the links in the description or the card somewhere here. So now that we understand what we need to do, we can go ahead and look at the code. So here we have the code and we have this function foreign dictionary. So the Leetcode function name might be different, but the logic is going to be the same. So we will first of all have a set nodes. In this set, we will store all of the letters that we can find from the words dictionary or the words list. So right now we have empty set for nodes, and then we are taking each word from the words list and we are figuring out all the character in that word, and we are adding those character inside of this set. Now even if we try to add the same character multiple times in the set, the set will only keep one value for that character. It will not keep multiple copies of that character. So that's why we are able to add characters easily. Now here is the part where we are actually building an adjacency list. So we have this adjacency list variable here, and it is basically a hash map. So what we are doing is we are initializing the hash map like this. So for each node in the nodes set, we are creating a list in this dictionary. So what it means is that each letter that is present in the nodes now will be present in the dictionary also as a key, and its value will be an empty list right now. And in the empty list, we will simply store the other character that we are connected to. So here we are figuring out the length of the words list, and now here we are simply figuring out the edges between the character. So we are taking two adjacent words here, word 1 and word 2, that are present at I index and I plus 1. And then we are figuring out the minimum length of the word between them, because we need to check for the invalid condition where a word is a prefix of the other word and the length of this prefix word is less than the length of the other word, but this smaller word is actually coming after the larger word. So that is the case that we are checking here. If that is the case, then we can simply return an empty string. Why? Because it is an invalid case. This should never happen. This is an invalid case. Now if this case is fine, we can move on. And now here we have a loop. So we are comparing the character between word 1 and word 2. So if the character at jth index at word 1 and word 2 is different, it is not equal, then we are going to say that the character in word 1 have an edge to the character in the word 2. Just like we did in the drawing explanation. We can have two words, HR and H and K, and we can find the first different letters. So it is R and N, and then we are saying that R have an edge to N. What it means is that in the list, in the adjacency list, we will have something like this. The key will be R, and it will have a list, and in the list we will store N. So it represents that we have an edge from R to N, and that is exactly what we are doing here. And once we find this character, we are going to break, and then we will come back here and we will go for the next set of words. Now after we have built our adjacency list, we have these sets. So these visited set, past visited set, they are actually part of DFS and topological sort, and those things are actually prerequisite mandatory things. You must know them before trying to solve hard question, because they are kind of just like they are the ABCs for hard question. You need to know them beforehand. So we have visited, we have past visited, and we have stack. Stack will store the topological sort. Visited set will store the node that we have already visited, and path visited actually stores the node that are on the current path that we are traversing. This is used to actually detect the cycles. Okay, and now here we have the DFS function. So we are taking a node or a character and we are checking if it is already in the path visited, we are going to return the true, which means we have a cycle. Okay, we have detected a cycle. It should not be in the path visited already. Now if we see that node is actually in the visited, we will return false. What this means is that we have already gone through this node in some other path, and now we don't need to go through this node again. Now if node is not in path visited or node is not in visited, then you will simply take the node and put it in the path visited, representing that now we are going through this node. And now you will go through all the neighbors of this node. And if at any point the DFS of neighbor actually returns you true, then you know that you have detected the cycle in the inner parts of the graph. So you can also return true from here. That is saying cycle detected in the child. Otherwise, you have gone through all the neighbors, and now you can actually come back here. You will simply remove this node from the path visited. You will add this node in the visited, and you will add this node in the stack, because it is a post order traversal. That's why you will add this node in the stack after you have gone through all the neighbors. Okay, all the neighbors should be processed first. Then only this node will be appended in the stack. And then at the end, we are returning false. False means that we have not detected the cycle in the graph. And now here we are actually using the DFS function to calculate the answer. So for all the nodes that are present in the nodes, we are going to run the DFS. So if the node or the letter is actually not present in the visited set, that means we have not gone through it yet, we can simply take that node or that letter and run the DFS algorithm on it. And if the DFS algorithm actually returns true, it means we have detected cycle somehow. So we will simply return the empty string here. Now if this entire thing actually runs before returning the empty string, we know that now our stack actually contains the topological sort. So we will simply take all the values from the stack, we will create a string here, and we will simply return that as the answer. So now let us try to submit it and see what happens. So yes, our code is accepted and we have passed all the 24 test cases. So now let us look at the space and time complexity for this particular solution. So the time complexity is order of n plus v plus e, where n is basically the sum of all characters that are present in the words list. So we can have multiple words like HR, then we can have RN, then we can have NN, okay, then we can have KP, then we can have PPK, right? So sum of all these characters. So how many characters do we have? Not the unique, the sum of all. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 11 characters total present in the list. So that is what the n represents. And we have this n here because we are running a loop in the starting to figure out all the unique characters from all these words, because those unique characters will actually be the nodes, right? The vertices or the nodes. So to run that loop, we are going to go through all the characters in this particular list, right? So basically we will run that loop n times, where n is the total number of characters in the given word list. Then after that we build the graph or the adjacency list, and then we are running the DFS on that graph, that is v plus e. The time complexity for running a DFS on any graph is v plus e, the number of vertices or nodes plus the number of edges between those nodes. Here v is nothing more than the letter that we have in the nodes set, and e is nothing more than the relationship or the edges between those nodes. So this is the time complexity, and the space complexity is actually order of v plus e, because we are actually building an adjacency list, and the adjacency list stores the information about all the vertices and all the edges between those vertices. So it is going to consume order of v plus e space complexity. So yeah, like the video, subscribe the channel. If you have some kind of question that you would like me to target, or you have some kind of topic that you would like me to talk about, just let me know in the comments. Now we will meet in the next video. Till then, bye.